Hey Shane,
Hey, what's up?
how are you?
I'm good. How are you?
It's been a stressful 2 days of moving in and getting everything ready, but
Oh yeah,
I'm really starting to come together and settle down a little bit.
it's good.
Yeah, so like I said, I really wasn't able to get much done the last few days. I had an interview this morning, so that was like I was doing a lot of prep for that.
How'd it go?
It felt like it went well.
Hmm?
It was one of those high reviews, so it's really difficult to tell,
Yeah.
'cause there's no person sitting there and speaking to you.
Oh, I see. This is for med school,
Yeah.
and you said it's higher view. Like,
That's apparently like I don't know. When my finance friends told me that that's a thing where like you just have like 30 seconds to look over a question, then a minute 30 to answer it, and then you go to a next one.
oh, I see. I see. Got it. A AI HR combination.
Something like that.
All right. So yeah, how are your like classes and stuff?
Well, my classes don't start until Monday, so for now I'm fine.
Yeah, got it. It's okay. Let's pick up where we left off. In
Were
that
we done with the Jack Weston? I can't remember.
Oh no, we were like on like around question like 80. We're almost done. We're gonna get it
Okay, I understand.
pretty much.
Perfect. Okay. Yeah, you're right. I'm on 89. Share my screen. Okay. Um, why is it? Because it's in Kelvin?
Probably actually. Yep. So yeah, so in general, Kelvin is
Mm,
to be like the SI unit. Um, so pretty much just that. And then yeah, just entropy is the Q here is the change in thermal energy. Um, NT is the temperature.
mhm. And then you still have to add 100 to it. So it's like S equals Q over T.
Uh-huh. Yeah. And yeah, when you convert from Celsius to Kelvin, you just add 273 to whatever it is at Celsius.
Uh-huh. Got it.
Hmm.
But how do we know that to do that? Because it says Q over T.
Hmm.
T.
Yeah.
So that's just what it is. It's like you take the boiling temperature and you add it to the standard.
Yep. So basically this mass of water with this latent heat, um, L,
Hmm.
goes at 100 degrees Celsius, and then the expression for the change in entropy is basically that formula. The
Okay.
Yeah.
Sounds good.
And this is just naming. Um, so
Yeah.
let's see, 5 methyl, 3 ethyl. So you, so like I would normally start off with the longest chain. So 1, 2, 3, 4, 5, 6, 7.
Hmm.
And then I could see that at the 5, or rather at the 3 position, there's, oh wait, so what I just did should be the other way around, because if you do it this way, you have this substituent here at a closer carbon.
But how come, like, don't you always go left to right?
Oh, no, no, no. because there is no real left or right, like
Mhm.
molecule could, be in any orientation, but you will go in such a way as to have the priority groups or, the other, the I forgot the word for it, but like substituent, I think. But
Uh-huh.
you want that stuff to be like as early as possible.
I
Um,
understand.
yeah. Like for instance, if I had this with an OH here,
You would make it on the two, not the three.
exactly. So three ethyl and then four dimethyl. And so for this one, it says that there's so this is like wrong for the reason of like the five here, but it's also wrong for the reason of it's saying methyl. We have a dimethyl here, but it puts the di in front of the ethyl, and we have our ethyl group here. So we should only have one ethyl group and then two methyls.
Got it.
Yep.
This is a complete guess.
So okay, so yeah, lactone. Lactone is a do you remember what an ester was?
So sorry. It was like something with alcohol, right? Like where it,
So this is part of like the carboxylic acid derivatives. So that's
yeah.
the functional groups that you'll see. So like for instance, they'll have a carbonyl group and let's just call this X, right? X, if it's an OH, would make it what? Like if this X was an OH group?
Carboxyl.
Yep, a carboxylic acid, right?
Yes.
Now, if it was just H, a hydrogen,
Isn't it carbonyl or
so the carbonyl is just the term for a carbon double bonded to an oxygen.
oh,
But but yeah, if it's just a hydrogen here, it'll be an aldehyde.
aldehyde? Okay.
If it's another like carbon group, which I'm just gonna write as R, it'll be a ketone. Um, if it is an amine, it'll be an amide.
Yes. That one I knew.
Yep. And if it's OR, like oxygen bound to some more carbons, it'll be an ester.
Okay.
So now a lactone is a cyclic ester. So a good example of that, or rather, yeah, so something like this perhaps, right?
Mhm.
Okay. So they're asking which of the following compounds will most readily form a lactone. So, okay, so we see that we have three choices that are acids, and then one choice that, so if it ends in ONE, what do you think uh that means?
We talked about this for something else, but I don't think that it applies here, does it?
So yeah, we've probably talked about it with like ate and ite and
Yeah.
us and ick. So yeah, the suffixes are going to give you a lot of information. So what functional group, you know, ends in ONE?
Lactone
What about
and
here?
oh, Ketone.
Yeah, good, good. So yeah, if it ends in ONE, it's a there's going to be a ketone involved. If it ends in AL, that'll be an aldehyde.
Mhm.
So okay, so we have our ketone here, and you know, it would look like one, two, three, four carbons for the bute part, and then, well, I guess just an OH group. So, would that likely like close in on itself?
Yes.
If it so,
No, it wouldn't.
mhm. So good. So we can get rid of the ketone one, and then for the different types of acids, we would know that it would have some type of carboxylic acid functional group
Yeah.
and also a hydroxyl group, right? And what I usually say, so what do I usually say about hydroxyl groups?
It's the most common functional group.
Most common nucleophile.
Mm.
So, and the most common electrophile is a carbonyl group,
Right.
right? So, if you had like some OH, like an OH group here, it would attack the carbonyl group.
So
Forming,
they need as much distance as possible, right?
yep, yep. And particularly, uh, if it forms a six-membered ring,
Which is no.
hexagon.
Hmm.
So, uh, yeah, like the story goes is like, the story goes like this. It's like, okay, they've tried to figure out, so they figured out like way back in the day, like the energy for different, for like methyl, for like ethyl, or ethane, propane, butane, etc. And they found that when it goes to like the energy level drops when it goes to like hexane, and then it goes back up as it goes to like heptane and stuff like that. So they didn't know why the six carbon molecule was so much more stable than the rest. There's a guy named Kekule who had a dream about something called an Ouroboros, which is a snake chasing its own tail.
Hmm.
Like, oh, that's why hexane is so stable. It's cyclohexane forming a hexagon, and hexagons come up a lot in nature. Like there's even one on top of like Saturn. Uh, Also like water molecules, when they freeze, they form hexagonal,
Hmm.
crystals. So if it's a pentanoic acid, it would be like, let's see, so one, two, three, four, five, and then the hydroxyl uh group. And so when that attacks that over there, it's going to make a six.
Close in on itself. It's gonna make, yeah, a hexagon.
Yep.
So looking at this problem, like saying I know the functional groups and everything is like in order, like I think that this would still be a pretty confusing question.
Oh, well, you in addition to the functional groups, if you just train yourself to, when you see a hydroxyl group, think
Mhm.
nucleophile. When you see a carbonyl group, think electrophiles. So
Electrophile.
if we're trying to form a lactone, which is a cyclic ester, and we're given all of these, molecules, it must form a bond with like intramolecularly within that molecule.
What is that butanoic acid?
So
This is propane and this is butane, right?
yeah, so prop is for 3 carbons, but is for 4,
Oh,
hence 5.
five.
Yep.
Okay.
Mhm. Yeah, chirality.
Well, I know chirality. Like this one, I was
Mhm.
like, if it's this order, then you count in the opposite direction.
Tell me what you
No.
about that.
Like you change their configurations. Like this has to be one because it's the one that goes out.
Well, so for each chiral center, so let's look at 1, for example. Um, the bond that they're not showing us, which would be like in black, would be,
Oh, so there's another one there that they're not showing.
yeah, right? There would have to be a hydrogen.
I'm thinking like when I learned this, hydrogen was the one that like weighs the less, so then usually it's four. So then if hydrogen is on the one, then something else like needs to be changed with it, switched with it.
Yeah, so basically what you do is you want to, if you have hydrogen pointing like into the page, um that makes it easy for us to do like, clockwise or counterclockwise. Um, but if it's pointing out of the page, we don't want that. So what we can do is we can do it the normal way and then like see if it's clockwise or counterclockwise, and then we can flip it.
Mhm.
So for this over here, I'll use blue. So we have our highest priority, which is going to be for this carbon. Well, actually, let me see. This is a methyl. This over here. So let me see what they wrote down here. Numbering points clockwise, priority 2 group points backwards. So chiral designation is flipped from R to S. And then this one numbering clockwise. None of the priority ones go backwards. So chiral designation remains R. So yeah, so okay. So they're doing that with, I'm not sure why they have this as the first priority, but yeah. So we have our hydrogen pointing front and like out of the page. And so whatever we do, we just have to flip it at the end. So
Mhm.
basically, if this is priority 1, and this is 2, and this is 3, and that produces a clockwise term. Clockwise would be R. And since we want our hydrogen to be into the page and not out of the page, we just have to flip this to make it S.
Okay.
And then for the carbon 2, it's going to be this as the number 1 priority, followed by this and that's clockwise. And this time the hydrogen is actually, they didn't draw it, but the hydrogen would be like the dashed line of
Yeah.
the page. So that's where, it's exactly how we want it. So we keep the R designation.
This second time, shouldn't it be like if we're doing from this? Shouldn't this be one?
Um,
Or we're doing it for this one.
from this, you mean?
Right. It's still on the dash.
Mm-hmm.
So you're treating these as two completely separate. So when you're looking at this one, this dash isn't here.
Oh, no, no.
I'm
It's there, it's there. So if we look at this carbon here, what we can do is we can just order it in terms of priority, and so we would get that type, a clockwise turn, with this priority being 1, this being 2, or rather, with this being priority 1, this being priority 2, this being priority 3. But since it is inside pointing inwards, and we want the hydrogen to be pointing inwards, not the priority group, that means we just have to flip it at the end.
Okay.
Mhm.
Yeah. Yeah. I went through it and I was like,
Mhm.
anomeric carbons doesn't work here. They're not enantiomers. I like went through it. I would like us to make sure that I know what
Mhm.
like I think it's like anomers are when it's the same like chiral carbon,
Mhm.
right?
Yeah. So the example for that is glucose, where you can have where this carbon is anomeric, and so the hydroxyl group can be like having this up, like it can be above the ring or below the ring,
Mm-hmm.
and that would be the different anomers. So
Right. Okay.
anomer would be at 1, you know.
Carbon. So there's monomers which are the same and then anomers which are different
So
at one carbon.
so like a monomer is just like, 1 unit of like a polymer, but here anomer is just, yeah, when you could have different chirality
Understood.
at one chiral center. Enantiomers are,
That's when they're like mirror images.
yeah, so that means that they will have opposite, stereochemistry at every chiral center.
Yeah.
And diastereomers would mean opposite uh stereochemistry at least one chiral center, but not all chiral centers.
Yes.
And then epimer is pretty much the same thing as, or rather, typically when we have a change in one chiral center, but it's pretty much a diastereomer that's in a straight chain.
Okay.
So,
All right.
mhm.
Surprised I didn't flag this.
Mhm.
Yeah. Oh.
Hmm. So, okay, let's talk about this. So, yeah, what are your thoughts here?
Um,
Mhm.
isn't there something with like double bonds being oh, wait, but no, double bonds are harder to break down, so why would that be the most rapid?
Mhm.
Like in like an enzyme substrate?
Okay.
I'm not sure.
Mhm. Yep. So, okay. Uh, to transition state during an SN1 reaction. So, what would so what do we do in an SN1 reaction? Or yeah, like how would you
This is biochem.
Orgo?
Really? Hmm.
Yep.
I remember learning it and I remember understanding,
Yep.
but I can't remember.
So okay. So we have SN1, SN2, and the key difference is that, so basically, oh, you remember like one time we went over like an orgo kind of thing that I wrote? And so basically SN2 is when you have a strong nucleophile that in one step comes in and forms a bond with the electrophile, and simultaneously breaks the bond with a leaving group. And so it happens in one step.
Uh-huh. Yeah.
That's preferred for like the electrophiles that don't have much steric hindrance, so like primary, secondary. But SN1 would be if there's a lot of steric hindrance, like tertiary. And so the nucleophile can't just come in because there's a lot of blocking. So it has to wait for the leaving group to leave first, and then it can attack. So
Hmm.
so
So D has steric hindrance.
yeah, so for instance, this bromine is at a primary position.
Mm-hmm.
This is at a secondary position. This is also at a secondary position. And
Tertiary, no?
this one, yeah, it's still secondary. Tertiary would be like,
I thought you were counting carbons, so it's like 1, 2, 3, or 1, 2, 3, no matter which side it's in the middle.
oh, it just so tertiary would be if it was connected to a carbon that was connected to three different.
Oh, okay.
Yep.
All right.
Yeah. So,
Then A is immediately out.
oh wait, yes, yes, yes. Good.
And then is it D because of the double bond?
Yeah, I believe so. Let's see. Most rapidly, because like we have secondary, secondary, and then we have this double bond here. And so I think that what could happen is if this bromine leaves, so when the leaving group leaves, by the way, you'll have a carbocation intermediate. So if you
Mm-hmm.
have a positive charge here, my guess is that maybe this can electrons from a double bond can go there and form something like this with maybe the positive uh charge there. But let's see what they what their explanation is. So okay. So
Rate limiting step is carbocation formation
mhm. And then that's dependent on the stability of the resultant carbocation and
by the number of alkyl substituents.
mhm,
Number of carbons increases the hyperconjugation.
yep, and then electrons
Further stabilize the
stabilize
positive
the positive
charge.
charge. So yeah, essentially when this, you know, breaks up or when the bromine leaves, it would be there would be a positive charge here. So
Mm-hmm.
electrons from this double bond can go and form a double bond here, stabilizing that.
So it's resonance stabilization.
It's not resonance in this case, but
It's just like
does
a
in
more stable
mhm.
molecule.
Yeah, yeah. Like if we have more electrons present at a region where it's a positive charge, it will stabilize that positive charge.
Got it.
And then they said electron withdrawing groups do the opposite, and that would be like um if you had like let's say a chlorine here and you have the positive charge here, the
Mhm.
chlorine will pull electron density towards itself and thereby make that positive charge even more positive.
Got it. Okay. Sorry. That makes sense. So I guessed this one, but I feel like if I draw it out,
Okay.
so it's on the 1, hexane is 6,
Mm-hmm.
like iodine.
Iodo. Mm-hmm.
Okay. So how does that look? Like,
Well, oh, yeah, sorry, go on. I thought you were drawing A, but no, you're drawing B, so you're on the right track.
Yeah.
So, yep.
Where does this part go? Oh, it's just at the end, I.
Yeah, so since we don't have anything else in the hexane, it could literally be anywhere, and we could just make that the one.
Right, but didn't we say that like if it's cyclical, it happens in one step?
Um,
Because that's what we want, right? We want it to happen in one step.
yeah, for an SN2 reaction, but not because it's cyclical.
Uh-huh.
So, okay. So, and then they're reacting it with potassium bromide, and
Uh-huh.
they're asking which would be most likely to undergo an SN2 reaction. So, you know, what we would want to see is like bromine or bromide ion coming in, attacking here, forcing that leaving group off for an SN2 reaction.
Uh-huh.
And so, it's okay. Now, what can help this process along is if this is a good leaving group or not.
Yeah.
Mhm.
So how do I know which ones are good leaving groups?
Uh, so okay. For the if you think about okay, so
Like,
yep.
is it the opposite of electronegativity or that not related at all?
Uh-huh. So uh yeah, that's exactly how you should be thinking. Good. Um,
Because iodine's at the end of it,
mhm.
and then F is the strongest.
Yep.
ONCl.
Mhm.
So yeah, so chlorine would be really strong, for example.
Mhm.
So
Yeah.
it'd be a bad leaving group because
Yep.
it wouldn't want to get rid of it. Like something like hydrogen would be good
Yeah.
or
Right. So if you open up the periodic table real quick for the halides, we can see that they go in order of like, okay, fluorine, chlorine, bromine, iodine, right?
Mhm.
Like, as we go down, we get less electronegative. Now, if the bromine is they're saying the reagent here, right?
So it's to be more less electronegative than bromine.
Exactly.
Got it.
Yep. You're on
Cool.
fire today. So,
Why aren't these flagged?
it doesn't say it's like.
I know, but why not?
I mean, I guess you got it because you got it right.
I think I was just stressed at the end and I
Yeah,
was going through them and
got it. So, yeah, okay. So now,
what is HI?
what do you
Heat interval?
think? So, what what other things could be up here?
Hydrogen, iodine.
Yep.
That's a reaction, and this is what it's reacting with. Okay.
Hydroiodic acid.
Okay.
Yeah. So okay. So now, yeah.
Heat.
I mean, it's good. You're actively thinking. Now, okay. So SN2 reactions, right? They will result in a single product with opposite stereochemistry. So an enantiomeric product. Um, whereas SN2 reactions would result in a racemic mixture of both enantiomers. So okay. So now, since we see that they're telling us that it makes this even distribution of product, we know that it's an SN what?
I think the going backwards thing is confusing me because is it SN2 since
So like, let's say we have this with a leaving group here and a nucleophile here. And so I think I described this before with like my hand. So like,
yeah, with the thumb.
So like, let's say that there's a leaving group attached on this end that you can't see. And then these are like the substituents. When you have the nucleophile approach, it will repel the substituents because it's forming a bond. The nucleophile is forming a bond with the electrophile. As the bond between the electrophile and the leaving group start to break,
Mm-hmm.
this goes like this. This is in the middle, the transition state. And then it'll go backwards like that, which will be essentially like my other hand.
Mm-hmm.
So with SN2, we have we invert the stereochemistry. So if this is,
So since this one isn't inverted, it's the
so,
same way.
so since
Automatically not SN2.
since SN2 inverts the stereochemistry, if you have, something like R enantiomer, it'll be flipped to S and vice versa.
Mm-hmm.
Now, okay, if you imagine the same thing, but with more steric hindrance, like, let's say like, we just have more steric hindrance here. You have to wait for the leaving group to leave, and then you'd have your intermediate. And then the nucleophile can attack from either end of that, or from either side of that electrophile.
Mm-hmm.
That's what makes it result in an even mixture of the R and S.
That's SN2, right?
So
This one.
SN2 is up here,
And this is SN1.
and then down here is SN1, yeah.
Got it.
And SN1, like,
And it looks like there's equal concentrations. So
yep, they're telling us that as well. Now, this is another word for this is racemic. Racemic.
mm-hmm.
And now the thing is with enantiomers, right? They rotate plane polarized light, like we call them optically active. So for instance, if the R enantiomer, right? Let's say it rotates plane polarized light clockwise, like 117 degrees, let's just say.
Yeah.
The enantiomer would rotate it in the opposite direction by the same amount.
Okay. Yeah.
If you're going from here to here, you're just going to see
No,
rotation.
there's no change.
Oh, sorry. So if you go from this to
But
this,
you're going, oh, that's just the angle. I understand. I thought you were saying like you go 117 degrees clockwise and then the same amount
oh yeah,
backward.
yeah. So now when you have a racemic mixture, though, that's what'll happen. You'll have 117 degrees going clockwise, and then 117 going counterclockwise.
To
You end,
balance it out.
yep. So you end up with it not being optically active.
Okay. Got it.
So if we look at A, it says optically active. That won't be
Mhm.
true, right?
Okay. Because you can't see a difference, right?
Yeah, because if they are producing an even distribution of the enantiomers that they'll cancel out.
Mhm.
Okay, now, so another thing about SN2 is
Back.
that it's a backside attack, yeah. So,
But if this is SN1, then we know that B is wrong.
correct. So it's like if the electrophile is like a person and walking home from I don't know someplace at night, the nucleophile is a bad guy and
An
comes
electrophile is good guy. Right.
yeah comes in from the back,
And it just, right.
etc. But if you have something like with steric hindrance, like if these were like methyl groups, the nucleophile is like, oh, there's too many friends. The person's with their friends. I can't do anything. So they're gonna wait until the friends leave or whatever, and then it'll attack. So, but yep, B is wrong for that reason. And then C, the transition state has partial bonds to the leaving group and the nucleophile. That's that situation where we have simultaneously bonds forming with the nucleophile as bonds are breaking with the leaving group. So that's also SN2. And then SN1 is the one with a carbocation. And if they're saying the rate limiting step, that can also be a clue because SN2 happens in one step and SN1 happens in two. And that first,
Right, there wouldn't be a rate limiting step for,
it'll be just the first, like,
right,
right?
that makes sense.
But yeah, the carbocation formation is what happens in SN1 for the first step. And that's an intermediate as well, which is
Okay.
yep.
Sounds good.
Mhm.
The following one, the concentrate will double the rate. Wouldn't they both have to go up because it's always balanced?
So so one of the most common things people ask is like, why is SN2 one step and SN1 two steps? Uh,
Because they probably discovered SN1 first.
so it has to do with the kinetics. So
Mm.
SN
I swear we learned this in biochem. Like,
yeah, they'll probably went over it in biochem also.
that's,
It's
I
like,
feel like this is orgo. And I was like, I didn't really
yeah,
take
yeah.
orgo, and I remember learning about.
Yeah, I mean, like, how I said before, like, biochem is an application of chem, and that includes organic
MS
chem.
bio and bios physics
Yeah,
or
yeah.
whatever the order you say it is.
Yeah, yeah. I mean, like, if you just like the easy way to see it would be like, okay, if you look at for bio, it'll be like tissue, organs, stuff like that. You can do like cell bio, right?
Molecular.
Yeah. And so like a cell, if you what builds up a cell? Molecules. What builds up molecules? Atoms. What builds up atoms? Uh, subatomic
Electrons.
particles. What builds up those? Quarks. What builds up those? You know, we can.
I get it. Yeah.
So that's like how if you wanted to figure out the order, that's like how it works. So, but yes, biochem, like of course, this stuff would also come up because it's still it's just chemistry applied to biological molecules. But yeah, so now the reason SN2 is called SN2 is because it has second order kinetics, which means that its kinetics will be dependent on both the nucleophile and the electrophile. And the SN1,
Where does the substrate come in?
oh yeah, so that when they say so yeah, that they
That's the electrophile?
yeah.
Okay, got it.
So yeah, so SN so here, this is the
Is
rate.
SN1 based on the electrophile then?
Yeah.
Okay, that makes sense. So it would be, for SN1, it would be A.
Uh-huh.
Got it. Cool.
Mhm.
Yeah.
So,
I'm still really struggling too.
uh-huh.
I guess HCl chloride makes sense. Like chlorine would be in it. So 3.
So okay, so let's think about what these look like. Um, so
I would start with drawing out this like acetic acid,
yep.
which I have no idea what it looks like. Wasn't
So
one of the ones we went over.
so what functional group do you think will be there?
Hydroxyl.
That's what you usually say, but
It's never right.
because the thing is, what is a hydroxyl?
An OH.
Yeah, but most of the stuff that we've been talking about
Carbons and
uh involve a carbon double bonded to an oxygen, right?
yeah, which
So
is yeah.
so that's why so you want to think first about that and remember how I wrote like, this would be for like carboxylic acid, this would be for aldehyde, this would be blah blah blah. So so if we're talking about an acid, it should have um a what functional group? Like which functional group
The
is an acid?
it was the first one you drew, right? The
Okay.
double bonded to an O.
So, all of the uh
it wasn't the ester, right? That was
no,
no.
it'll be the one that's literally called acid, carboxylic acid.
Which was the carbonyl linked to an oxygen, right?
Uh,
Bonded to an oxygen.
kind of.
No. The R group was the ketone.
Yep.
The OH was hydroxyl.
So I think you're conflating hydroxyl again. Like OH on its own is hydroxyl, but when the OH is attached to the carbonyl carbon, what is that?
Carboxylic acid,
Yes.
which is what you're looking for here.
Yeah, yeah. So an acetic acid would look like basically that, right?
Yes.
All right. And what are we adding to that?
Propionyl chloride.
Mhm.
Is that like 5 or propane?
Mhm.
So PCl,
Wait, what? What's the P?
propane.
What? But would you write like what is propane made of?
Gas.
So so okay, so like alkanes. You said you took organic chem, right? But it was like it was like
It was a summer course.
uh-huh. So so like an alkane, do you know like what that is?
Not like visually, no. I don't know any of them.
Hmm. So okay. All right. So basically, okay. An alkane is just a regular like hydrocarbon consisting of carbons and hydrogens. So the first one would be methane, which is CH4.
Yes.
Now, if we have two of these combined, like CH3 combined with CH3, this is ethane. Okay, with two carbons. Yeah.
But we're looking for alkane. So that's like an alkyl.
So alkanes are what these are.
A methane? Oh, they're just both types of alkanes.
Yep, yep. All like octane is an alkane. All these things are
Pentane. Or sorry.
pentane, yep, butane, all that stuff. These are what alkanes are.
Mm-hmm.
Now, uh, so now the F part is referring to two carbons. Prop refers to three carbons. But refers to
Four.
four. And then after that, it's like more logical with like pent, hex, etc. So propanoyl chloride, right, would be having how many
Three.
three carbons, right?
Yes.
Okay. So
Three carbons linked to a chlorine or
uh-huh.
uh-huh.
So you
So
yep, go on.
let me just try to draw it. Which is minus, right? This is, I mean, there has to be a positive charge here.
Yeah, so now I should also say something about the suffix here.
Chloride
Oh, the
or oil.
uh like the oh sorry, of the propionyl chloride.
Mm-hmm.
Um that essentially just means that there's in the carboxylic acid derivatives, there's one that I didn't write. It's when you have an acyl chloride and it looks like that.
Mm-hmm.
And that's one of the like carboxylic acid derivatives that's the most reactive. Um so propanyl chloride would look like this with another one attached. So pretty much what you let's see, one, two, three, yep, and then it'll just be like that.
Mm-hmm.
Yeah. So the reaction between acetic acid and propanoyl chloride is going to be, yeah, mixing these.
So does the hydrogen come off? Like where do you lose the Cl and the OH to? Oh, that's where HCl comes in,
So yeah, so if we,
right? And then you have the double bonded oxygen,
yeah,
something like this.
yeah,
So it's literally just the two results are
yeah,
this and this.
yeah. So tell me what happens in this reaction here.
So they're like drawing it flipped of what we did, but you have, sorry, my intake came out. You have your O. I really suck at drawing this. OH and you lost the hydrogen, it came off. So you have the oxygen on its own, and then, but don't we have an extra carbon? Like, wouldn't it be? Oh, yeah. Like, we have it like this.
So tell me what. Oh yeah. So wait, are those
Like,
are you are you drawing that as like
or no, I guess I do.
down? Is this like one?
Oxygen is here.
Is this
I'm confused.
is this entire thing connected?
Well, I'm trying to connect them,
Okay. Yep.
right? But I'm just trying to like
Mm-hmm.
flip it so it goes down, up, O,
Mhm.
Cl.
Yeah.
But I
Now,
feel like we have an extra thingy
so
than
what are we attacking?
carbon.
Like, what is attacking what?
Doesn't the acid usually attack?
Tell me, like, tell me about that.
Well, acids are
So think about so for this.
acids are proton acceptors.
Hmm,
Or no, proton donors.
redundanters. Yep.
Is the base ones. Yes, okay. So since it's an acid, then it's,
So
or no, I guess it would be attacked.
so 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 let's see, right? So over here, just tell me a little bit more about what you're doing.
I was like just adding them together.
Uh-huh. And I'm just curious about this part.
Well, because I know that there's equations where like when you're combining it, like you take out the hydrogen from one side and the like O from another, the OH and the H, and you end up with like H2O leaving, and then you combine them both. But
Uh-huh. So
that's what I'm assuming something like that happens with the HCl,
so
which is why it's flipped.
yeah.
The hydrogen and the chlorine need to be next to each other.
Yeah, so don't worry about these yet right now. So we want to see what happens when we mix this acetic acid with this propanoyl chloride. So well, these let me erase yours thing, but like this, the charges here won't be there. So I'll just make a white thing on top of it. Now, because okay, so now this chloride, what do you think that does to a molecule?
I'm not sure.
So, what is chloride? I guess, like, what is like a property of it that you can tell me based on the periodic table?
Oh, that it's electronegative,
Good.
which means that it's like a strong acid
So now,
and a bad leaving group.
so if we know that in a carbonyl group that we have a carbon double bonded to an oxygen, since oxygen is electronegative, it pulls electron density from the carbon towards the oxygen, giving you a partial negative, partial positive, right? Partial negative for the oxygen, partial positive for the carbon, right?
Yeah.
Now, that happens just from a carbonyl group. Now, if we have a chlorine attached, which is highly electronegative, even more so than oxygen, it will pull electron density
From
also.
the oxygen,
Oh no, from the
just
carbon.
still create the partial positive, partial negative.
Yep. So now the carbon of the carbonyl group that's attached to the chloride is even more partially positive, right?
Got it.
Which means that like the entire reason that the OH group attacks this is because it's partial positive. So if we made it even more partial positive, this guy should attack that right there.
Okay.
Right? Because this carbonyl carbon here is,
How do you,
yep.
okay, that makes sense. So they're both getting attacked, they're both creating partial charges. But what is the relationship between the OH and the chlorine?
Oh no, so
They both get pulled off then?
okay, so tell me why it would attack the partial positive.
Because it's electronegative.
Mm. So the electronegative, so the carbon isn't electronegative, right? Because if it was, it should have partial positive, like negative charge, right? So a nucleophile, right, is a Lewis base, which means it's an electron pair donor.
Uh-huh.
So if you had a neutral charge and a positive charge, which one do you think the nucleophile will donate electrons to?
The chlorine.
No, no. So I'm saying, let's say you have a neutral compound or a molecule or whatever, and then one with a positive charge, let's say another one with a negative charge. Which one would be most likely for a nucleophile to donate electrons to?
The negative.
Um, what charge do electrons have?
Negative. But, oh, so try to balance it out and donate to the positive?
Huh? Because it wouldn't donate to the negative because negative already has electrons, right?
Yeah.
So it'll donate to the positive, right?
Mm-hmm.
And that's also in the name nucleophile, like the nucleus of an atom is positively charged, right?
Yes.
So nucleophile likes positive charges, right?
Okay.
And an electrophile likes negative charges, right?
I know. I'm sorry. I'm like completely,
What's up?
I don't know. It's like not sticking in my head at all. I'm like,
All right,
oh,
let's
what's going on?
sure. So let's not worry about this problem right now. Let's just talk a little bit about the electron pushing. So, um, okay. Now, if we had a carbonyl group like this,
Yes.
the oxygen. So, what is meant by electronegativity?
Um,
Mhm.
Stability of, I don't know.
So, let's open up the periodic table. All right. Now, what's the trend for electronegativity?
FONCl
I mean like the periodic trend.
goes down.
Uh, so
Or I guess no, it goes to the left.
okay, there's two, so there's one that goes this way, up and to the right.
For electronegativity?
Yeah, this is for electronegativity, this is for ionization energy, this is for electron affinity.
But wouldn't that mean that like, oh, so the end result is that like F is the most electronegative if it's going up and to the right?
Yes.
Okay, that makes sense. Yes.
Yeah. So this is definitely have to know this. This is from like
Yeah.
so definitely have to know the periodic trend here. So now there's one going in the opposite direction, and that's for atomic radius.
Yeah.
Sorry. So that must mean that okay, so it's okay. Now let's think about what electronegativity, ionization energy, electron affinity, what that stuff means. So let's say we have something like sodium, right? Now, in order for it to or to be the most stable form, what would it do? Would it gain electrons or lose electrons?
Gain.
So, so it would have to gain one, two, three, four, five, six, seven electrons.
Versus lose two to get to F.
Well, so everything wants to be like a noble gas.
Right. But so it's hard to go from like past the noble gas, right? Like once it gets to neon, it won't want to go to fluorine.
Exactly.
That's why I said gain. Yeah.
Well, if it gains, it would have
It
to gain
goes.
7 electrons, but it can just lose one to have the configuration of neon.
But I thought that
Like what type of
what would neon give us? Because the
uh,
noble gas, like what is like a noble gas relative to like electron negativity?
so the noble so everything wants to be like a noble gas in that it wants to complete its octet, meaning 8
So
electrons
there's no charge. I understand.
per shell,
Hmm.
right? So
Yeah.
sodium makes if it loses an electron, because if it gains electrons, it'll be negative.
Hmm.
But we don't ever see negative sodium, right?
Right.
So think about it like this, right? If it gained electrons, it would have to gain one, two, three, four, five, six, seven to be like argon, right?
Hmm.
But it's easier for it to just lose one electron to be like neon, right?
Yeah.
Okay.
No, this I totally understand.
Oh,
I was just like,
did you said that it would
I
be
have my order of like, the one that I memorized in my head of electronegativity, and I was like, oh, look, neon's not on there, so it has to go towards like either fluorine or chlorine.
well, that's why it's important to understand
Right.
it conceptually.
You
Because if
gotta, I understand.
you rely on
Okay.
memory, then you're gonna make mistakes like that. And
Hmm.
so, okay. So now let's talk about um oxygen.
Yeah.
So what does it want to do?
It still wants to go towards neon.
Right. Now, would it do that by losing
Gain,
electrons or gaining?
gaining.
Gaining, right? Because what it can do is if it lost electrons, it would have to lose one, two, three, four, five to be like helium.
Hmm. Yeah. So
But
it's
it's
a lot easier to gain.
for it to gain to go to the right. So that's why the trend is electronegativity goes up as you go up into the right.
Got it.
Now let's think about what does that mean about electronegativity, right? Like what does that mean? So it means like so electronegativity is a measure of how strongly something pulls or takes electrons to for itself, right? So the more electronegative something is, the more electrons it will take. And so if you had like HF, right? The fluorine, so like hydrogen has electrons, fluorine has electrons, of course, but the fluorine is so much more electronegative that it would be more so like the electron cloud would look like this. It would be predominantly around the fluorine.
Okay.
Yeah. And that means that this fluorine will have the partial negative and the hydrogen will have a partial positive because if it pulls electron density, like from the orbital towards itself, it will give itself a partial positive charge because if it can't get a full negative charge, right? Oh, I said partial positive, I meant partial negative. If it can't get a full-fledged negative charge, it'll do the second best thing, which is a partial negative. So that's why the carbonyl group is so widely seen on the MCAT and pretty much everything, is because the oxygen is more electronegative than the carbon, which means it pulls electrons from that carbon towards itself. That's why it produces this partial negative oxygen and partial positive carbon. Okay.
That makes sense. Yeah.
Now, if we have the same thing, but we have this with like a chloride, now we have like electron density of the carbon being taken by both the oxygen and the chlorine, making this partial positive even more partially positive,
Mm-hmm.
right? So now nucleophiles will attack the partial positive charges like this, and that's why what we see. But if we had this over here, it's even more partially positive. So if it was given the option of both of these, this is the one that it would attack. Okay.
Yeah.
So okay, so now let's you can close the periodic table. So now if we had our acetic acid and if we had our propanil
Fluoride.
chloride, like so they both have carbonyl groups, fine, but
The chlorine is more electronegative than the oxygen in the OH.
yep. So this
So
uh-huh.
so yeah, there would be the partial negative, partial positive for both of them.
Yeah. So for the carbon here, it's going to be like extremely partial positive because you have electron taken by the oxygen in addition to the chlorine. So that partial positive is where the nucleophile, in this case, this hydroxyl of the carboxylic acid, is going to attack that carbonyl carbon,
Mm-hmm.
right? Right.
Yes, I literally falling asleep.
So,
What's going on?
so okay. So now let's see. So if it forms a bond here, right? We can draw that. So like that's why I was asking about what you were drawing, because you have, you're on the right track in that you're
So
having.
because of the like extreme partial positive, that carbon basically disappears when you're drawing it?
Oh, no, no, no. So it's
Or
it's going to be the one that this oxygen binds to. So it's going to be like this. So I'll mark it in pink. So this is the carbonyl carbon,
all right, so then the oxygen, the double bonded oxygen goes on top of it.
is the carbonyl uh
Mhm.
carbon, and then it'll push this
Yeah,
up there, and
the
this.
Cl, but that Cl comes off as well.
So now this will just be like um so 1, 2, it's attached to two other things like that, and then a double bonded. I'll just try it like, whoops. Then this is that part, and then this should be, actually the way that I drew it the first time should be fine. Like that.
Can you just quickly explain what happens to the chlorine? Like because of the resin, like this whole switch thing, that's when it comes off?
Mm-hmm. Yeah.
Okay.
So yeah. So like if I so yeah, when it binds to this carbonyl carbon, it would push, or I'll do the intermediate here. So this would be, so the oxygen would be it would be an O negative, and then we have this ethyl group there, and the chlorine here, right? This would be the intermediate. Like right as this step happens with the OH bound to the carbonyl carbon, we have here.
Mhm.
But what'll happen is the negative charge will go back to recreate this double bond, and it'll kick off this chlorine as the leaving group. So that's why you'll end up with a molecule that is like this.
That makes sense. Okay, and then that's where the HCl comes in,
Well, that's where,
because we
like,
lost the hyd.
uh so that's where, so like which of these products here does this look like?
The first one. It's
Yep,
just flipped.
good. And then yeah, as you said, the chlorine leaves, and that could just be uh it can bind with or react with water to give you HCl. It won't do that normally, but since they're saying this is an aqueous acidic solution, then that means that the Cl minus would bind to H plus to give us the HCl. Yeah.
Okay.
So yeah. Um yeah, I think Orgo stuff would be good.
Wait, yeah, I really need to go over. How do you suggest I do it? Should I do like the blueprint videos or
Um so I'll try to think of a good way to do it.
or should we
But I would,
please stop?
with it.
I genuinely I don't think I can go until 3.
Oh, uh, okay. So
I'm sorry. I really like I just
sure, it's okay.
I'm
So
trying. I'm like I really tried to push myself through, but it's not working.
yeah, no, you're okay. So that other resource was the what was it? MCAT review.org. I think that
This
would
one.
be a good fast.
No, no, not this.
Oh yeah, it's I think it's a light bulb.
Yes. here.
Yeah. So
So there's other categories like organic chemistry, just go into this one.
yeah, this one I specifically think is good for organic chemistry. So for instance, so go down a bit. Some more. Yeah. Start with this. See it says hydrocarbons, right? So that involves alkanes, right? And then you'll go to the oxygen, so the alkane hydrocarbon. Then you go into the oxygen containing compounds, so alcohols, and keep going. Aldehydes and ketones,
Mhm.
carboxylic acids, right? And then you
Acid derivatives.
derivatives.
Yeah, esters, keto acids, amines. We've talked about all of this, so I definitely need to give it a read.
Yeah, yeah, definitely. So like,
Okay.
yeah, before it was just like the carboxylic acid derivatives, but you also need to learn about like alkanes and stuff. So I would look at this first. And then if you want like videos for it, um, I can look into that as well.
Okay.
Um,
Sounds
so
good.
okay, so yeah, are we
All
still
right.
meeting tomorrow at
Yeah, definitely. I'm just-
30, 4:30?
Yeah, I just, with like Shabbos, I wanted to stop like right before, so that's a good time.
Oh
And
yeah,
then
again.
I'm looking at my school calendar.
Yep.
The only time I can see an issue so far is on Friday. I have you scheduled from one for one, and it looks like I have a class until 1:10.
Huh?
So I might just need to move back a little bit if it's possible. So I can still take it from there. I can just sit in like an office space in the building or something.
Uh-huh.
Or I can just wait until I get home and drive home. I don't know. Whatever's like best for you on Friday.
Yeah, like
30th.
we can start um like you said like 110 or 120 or something.
Sounds good. Okay. All
So
right. So
okay, so I'll put it in for one uh
like
10.
1:15 even. I need to leave class and sit down somewhere.
Got it, got it. Now but what you should also do is because
Book out the rest. I think I have
yeah,
it booked until like all the way through to the exam. I just wanted school to start and to see how like the
I you only
uh,
book as far as I think let's see the 20
I think the 30th was the last day that I
30th.
booked.
Yeah, yeah. So you want to book, especially considering now that you have more limited availability. So you want to like book on like all the days till your like exam essentially because
Good.
they get
Yeah.
booked up. So you should do that like as soon as possible.
All right. I'll go into the Calendly now and do it.
All right. All right.
Okay.
Take care.
All right. Hi, Shane. Sorry about today. I just
No, 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 you're good. You're good.
yesterday was so stressful. I think it's still like carrying over and I'm
Yeah,
still tired.
totally. Yep.
Okay.
Get some rest
All
and all.
right.